Our next notion is to discuss when the inverse actually exists. What kinds of functions actually have inverses? You'll recall earlier I was always qualifying by saying if the inverse exists. Well, now we're going to talk about that for just a bit. One of the things I think you'll recall from your basic study of functions in an algebra course is one of the most basic ideas of a function, and that is to say that one domain element may not go to more than one range element. What you are not allowed to have happen is A mapping to two different places. The requirement is that each domain element must correspond to exactly one range element. In this case, it corresponds to 2. Now, we can see this geometrically because if you were to allow A to go to B and also A to go to C, then you would have the points A comma B and A comma C. And if you were to plot these points, let's suppose this is A, here's B, and here's C. Then you would have a point at A comma B, and you would have another point at A comma C. And what would be true of these 2 points, no matter what else is happening with the function, is it clear this would violate the vertical line test. In fact, that's where the vertical line test comes from. The fact that this is a violation of the definition of a function means that you're not allowed to have repeats in the first coordinate. That's a violation. And that means that in the graph, you're not allowed to have points vertically aligned. That's a violation. So anytime you're dealing with a function, you are not allowed to have one element going to 2 different places. Now here's how that plays into the ideas of inverse functions. Suppose I have A and B in the set A, in the first set, and set value little c in the range, set B. And suppose we have this, A goes to C and B goes to C. Now what does that correspond to? That corresponds to the points A comma C and B comma C. We do not have one element going to 2 different places. We do not have repeats in the first coordinate. We do not have points that are vertically aligned. So in terms of function f, there is no violation here. In fact, this could be familiar. If this is the function x squared, and this is the number, let's say, 3, and this is the number -3, and this is the number 9, then certainly 3 squared gives you 9, -3 squared gives you 9. Nothing untoward is happening here. But suppose, in this instance, we tried to construct the inverse function. Now this is the domain. Now this is the range. Now we're trying to map C would go to A and C would also go to B. If this were allowed, then we would have C mapping to both A and B. You would have C. Let's just redraw the picture. This is C, this is set capital B, this is set capital A. Here's little a, here's little b. If we allowed this inverse to happen, then you would have 2 arrows leaving C. As we saw in the previous example, that is a violation. Similarly, this would correspond to having C, try that again. This would correspond to having C comma A, and input, output, and C comma B, input, output. Notice, in this scenario, we have repeats in the first coordinate. That's a violation. And if you were to allow this, that would correspond to, here's C, here's A, here's B. These points are now vertically aligned. We have violated the vertical line test. That's a violation. Now, where did all of these violations arise? The only reason these are here is because in the first place, we allowed A to go to C and also B to go to C. Now, if all you're talking about is function f, if all you're talking about is a function, then there's no problem with that. But if, and this is where we're going to be going with this, if you want to include now and begin to discuss the notion of an inverse function, then that is not allowed. Because anytime you allow this to occur, that causes this to occur in the inverse, and that's a violation. This is not a function. In order for f to be a function and f inverse to be a function, in order for these inverse functions to exist, you are not allowed to have two different values going to one or more than one point on the range. And so, what then would be the requirement? In order for inverse functions to occur, so think the problem. You're not allowed to have two arrows leaving A because that violates function in the first place. Neither are you allowed to have two different values going to a single point. That would be a violation. And so what would be required is something like this. Each domain value goes to exactly one range value, and each range value corresponds to exactly one range value. One here goes to one here. You can't have two values going to one. You can't have one value going to two. One value in the domain goes to one value in the range, and vice versa. Because now, if this is function f, then we have a comma c, and we have b comma d. No repeats in the first coordinate. We have a and b. We have c and we have d. A comma c, b comma d. The vertical line test is not violated. And when we form the inverse, now this is the input, this is the output. That corresponds to the points c comma a and d comma b. Remember that if these are coordinates of the original function, interchanging them as coordinates in the inverse function. Notice we have no repeats in the first coordinate. That means this is fine. There's no violation here. And then this would correspond to C and D and A and B. So C comma A, D comma B. We have vertical line test happening. No, everything's fine. So the moral of the story is this. One domain value goes to one range value. One range value goes to one domain value. The phrase we use for this is one-to-one. The phrase we use is one-to-one. In order for a function to have an inverse, it must be one-to-one. One value here goes to one value there, and one value here goes to one value there. It must be one-to-one. Now here's how the graph manifests itself. In order for a function to have an inverse, the function must be one-to-one. One-to-one. Now, how does that manifest itself? Well, it must pass the vertical line test. But do you recall the violation a while ago? The violation earlier was the inverse doesn't exist if you have lines or points that are horizontally aligned. In order to satisfy this requirement, not only must the function pass the vertical line test, what does the vertical line test check to see? That checks to see if it is a function. If a curve fails the vertical line test, it's not a function, and we haven't been talking about it in the first place. So vertical line test must be passed in order for it to be a function in the first place. But in order for the inverse function to exist, it must also pass the horizontal line test. And it is done in essentially the same manner as the vertical line test, except you're doing it horizontally. And if it passes the horizontal line test, that means it has an inverse. A function has an inverse if it passes the horizontal line test. A function does not have an inverse if it does not pass the horizontal line test. Vertical line test checks for functionness. Horizontal line test checks for inverseness. If a curve passes the horizontal line test, it corresponds to a function. If a curve passes the horizontal line test also, then it is a function that has an inverse. It is possible for a function to pass the vertical line test, but fail the horizontal line test. One of the most basic functions you know is the square function. This passes the vertical line test, but it's clear it fails the horizontal line test all over the place. It passed here. It is a function, but it does not have an inverse because it fails the horizontal line test. Other curves in your experience behave like that. Consider the absolute value function. It passes the vertical line test, that's why we call it a function, but it fails the horizontal line test. The absolute value function does not have an inverse function. The sine curve passes the vertical line test. It is a function, but it fails the horizontal line test. It does not have an inverse. In fact, if you draw the entire graph of all 6 trigonometric functions, all 6 trigonometric functions will fail to be one-to-one. Now, you might be happy with that, but here's one thing we can do. Consider the parabola again. Suppose, for reasons we will consider later on, suppose we want to consider this function, but we only want it for non-negative values. We do not want to consider the negative numbers. Why we're doing that is we're going to kick down the road for now. But let's just suppose you want to consider this function on that interval. Well, now, this piece of the curve vanishes. And now, under this restriction, the curve does pass the vertical line test. It is a function. It does pass the horizontal line test. This curve does have an inverse. This procedure is called restrict the domain, or restricting. We have restricted, this is restricting the domain so that it does have an inverse function. So, a function is one-to-one, means it passes the horizontal line test, that means it does have an inverse. Okay, so the next video we'll kind of pull all this together and get some basic information about how we're going to use it.